Hi, my name is Pulkit Rustagi and I'm a PhD student at Oregon State University. Today I'll be presenting our work on multi-objective planning with contextual lexicographic reward preferences. I'd like to acknowledge my co-authors Yashwanti Anand and Sandhya Sai Subramanian. Agents in the real world require to plan over multiple objectives whose preference ordering can vary based on context. Consider the example of autonomous navigation through a city with urban construction and highway regions, and consider objectives like minimizing time to destination, maximizing pedestrian safety, and minimizing travel over uneven road surfaces. Depending on what part of the city you're in, the preference ordering over these objectives changes. And this change of preference we denote using a context. Context is an exogenous variable that defines a unique preference ordering over objectives. So in this example, the set of contexts are highway, urban, and construction. Given that an agent can encounter such scenarios in real life, how to plan for such settings with coexisting preferences is our motivation. Among multiple approaches to multi-objective planning, we use lexicographic optimization, where the preferences are indicated by an ordering over the objectives, showing priority, because it is intuitive, scalable, and guarantees a solution. Current approaches to context-aware planning in multi-objective scenarios include maintaining scalarization weights for each state indicating preferences at that state, or maintaining multiple orderings over objectives in a partitioned state space. All in all, these approaches typically support only a single preference ordering over the objectives or lack a systematic mapping from state to respective objective ordering. We formulate this problem as a contextual lexicographic Markov decision process, or CLMDP for short, which is represented by this tuple, which includes a set of contexts in the environment, lexicographic ordering over these contexts, set of objectives, set of lexicographic orderings over these objectives, a function to map a context to its respective ordering over the objectives, the model variables that include state space, action space transition, and reward vector, a function to map the context to its specific reward vector, and a function that maps state to context. So our approach has three main steps that are also shown in this figure below. In the first step, we compile a global policy from independently computed context policies, and in the next step, we check if there are any conflicts in this policy. Conflicts are loops or cycles that make the goal unreachable. If there are any conflicts detected, then in the next step, we try to resolve them by updating policy of lower priority partitions, mainly with the aim that the operation in higher priority partitions is preserved. For settings where state to context mapping is unavailable, we learn it using Bayesian inference on a set of trajectories provided by an expert. So the probability that C is the context for state S, we can break it down in terms of probability that can be computed from the data set that the expert provided and information from the model. And we can also generalize it to unseen states assuming a uniform prior. For our experiments, we evaluate in terms of performance in all objectives, consistency, and how the approach handles conflicts. Our approach is able to perform well across all objectives, as can be seen from this heat map depiction, where a darker color indicates higher objective value. Our approach also shows consistency in performance, where the minimum performing objective value using our approach consistently outperforms all baselines. And our approach is also consistently able to resolve all conflicts and reaches the goal every time. We also perform hardware experiments using a mobile robot, and we are able to show that our approaches, both through known mapping and through learned mapping of state to context, outperform other approaches. And we are able to validate our simulation trends using a physical robot. In conclusion, our contributions include formalizing the problem of contextual preferences over objectives as a CLMDP. We provide an algorithm to compute conflict-free policies with theoretical guarantees, details about which can be found in the paper. We provide a Bayesian approach to infer state to context mapping in settings where it's not provided, and empirical evaluation using a physical robot. For future work, we would like to extend our algorithm to non-stationary settings. More details and cool videos for our robot experiments can be found out at the project website linked through this QR code, and I would like to thank Office of Naval Research for supporting this research. Thank you.